We're learning about polar and nonpolar bonds right now, and it's important to be able to distinguish between the two. It helps us better understand properties of molecules. And so we're going to take a look at this organic molecule called propanone, which is C3H6O. And we are going to try and figure out the electronegativity differences for each bond. If we can do that, we'll be able to identify the bond as to whether or not it's polar or nonpolar. Remember that polarity of bonds relates to how electrons are shared between them, right? If we get equal sharing, that's a nonpolar bond. If the electrons get pulled to one side of the bond more because one atom attracts them more, then that's considered a polar bond, right? So we're going to take a look at this organic molecule propanone and try to figure out what bond types are there. And for any polar bonds, we're going to draw in the bond dipoles where needed. So we've got a number of things happening in this problem. So let's start with the first part, electronegativities and identifying bond types, because those go hand in hand. So let's look at the different bonds. I see a C to H bond in the molecule. So we can figure out the electronegativity difference for the C to H bond. Remember that it's the absolute value of the electronegativity of the first element, so let's just say carbon, and subtract the electronegativity of the second carbon, or the second element in this case, which is hydrogen. Now these bars I put on either side just mean absolute values. So that just means no matter what we get as an answer, we always want the positive value of it. So if you do calculate it and you get negative, just change the sign to positive. That's all that's going to mean. To avoid that, just put the element with the higher electronegativity first, and then you'll always get a positive answer. So we need to figure out the electronegativities of these things. So that's where we're going to look at our chart. Hopefully you've printed this off and you've got it with your notes. But here's our chart that we're using for our electronegativities. And I'm just going to move my image down there. So we're looking at carbon. Carbon has a value of 2.5. And hydrogen has a value of 2.1. So those are the two values we need to be able to calculate this particular problem. So getting back to the problem then, we are going to take our 2.5 and subtract our 2.1. That's going to give us our absolute value bars. And so that would give us a value of 0.4, which in this case, when we talk about the carbon to hydrogen bond, that's telling us that there's a little bit of unequal sharing of the electrons, but it's not big enough yet that we would classify it as polar. So this ends up being a nonpolar bond. Okay. So we've worked with one bond so far, the C to H. Now let's look at C to C. So carbon to carbon, I'll do that one over here. We want to find the delta En, so the electronegativity difference. Remember, just delta means difference of the carbon to carbon. So again, electronegativity difference carbon. So we want the electronegativity of the carbon, subtract the electronegativity difference of the carbon, which is going to be 2.5 minus 2.5, which equals 0. So that tells us with 0 that we have equal sharing, which makes sense because both atoms in this bond are carbon. So this is a nonpolar bond. So we've got two nonpolar bonds in there. We've got all those carbon to hydrogens are nonpolar, the carbon to carbons are nonpolar. The last thing we're going to look at for our bond type is our C double bond O. Now, being C double bond O, we don't have to worry about the double bond. We're looking at the two atoms involved. What's the pull of the electrons, right? Electronegativity tells me who wants those electrons more in that bond. So when we calculate the electronegativity difference of the C to O bond, again, I'm going to go to my electronegativities. Oxygen is 3.5, carbon's 2.5. So when we do this, the electronegativity of the oxygen minus the electronegativity of the carbon, and 3.5 minus 2.5, absolute value of that is just 1.0. So that is high enough now. Remember, as soon as we get larger than 0.4, we're talking about polar bonds. So the C double bond O is a polar bond. And for any bonds that are polar, what we can do is we can then identify the dipoles. So because it's polar and the electrons are unequally shared, one of those atoms is pulling the electrons towards it. And if it's got that stronger pull, it's bringing those electrons closer to it, means it's going to feel like it's more negative, right? It's no longer neutral anymore because those electrons are constantly found closer around it. So it's pulled extra electrons closer to it. So it's going to feel partially negative. So when we look at that value for oxygen of 3.5, since it's got a bigger electronegativity, it's got a stronger pull on those electrons. So the oxygen side of the bond is going to feel partially negative. So we use this partial dipole symbol. It almost kind of looks like a music note, and then we put the negative to say that's the negative side of the bond, and the carbon would be the positive side of that bond. So the electrons aren't as close to the carbon. They're being pulled away from the carbon, so the carbon's going to feel like it's kind of lost some electrons. That's why it's partially positive. So we can indicate the dipoles on that diagram. So when we look at this structure, we've got some nonpolar regions where the carbon and hydrogen are, but we have this polar region of that carbon to oxygen. And that's going to change the properties of how this thing behaves relative to a normal, just straight up hydrocarbon with 3 carbons in it. And for those of you that are wondering, propanone is a very useful thing in everyday life. It's what we use as it's acetone, also known as acetone, and it's used in all kinds of products. But one of the biggest uses is in the nail industry as a nail polish remover.